Hello everyone, we are Group 11. Here are my group members. We chose ogbn-arxiv for our project. First, let me introduce the ogbn-arxiv dataset, which represents the citation network by MAG. We need to solve a 40-class classification problem and predict the primary categories of the archive papers, given its features. We try to use Gcn as a main method to solve this problem. Let's give a brief intro about Gcn. At first beginning, we only get one graph. To specify the mode and even to predict the node property, Gcn transforms the nodes and edges info into feature matrix and adjacency matrix respectively. Once the graph information has been converted to matrix information, it is possible to draw on the CNN. We need several hidden layers to robust the process. In each layer, Gcn aggregates the node's information using propagation rule to form the characteristics of next layer. Let's now look at the core of the Gcn. This formulation. The description of each variable was shown as the following part. Each layer of the Gcn is multiplied by the adjacency matrix and the feature matrix to obtain a summary of the features of each vertex's neighbors, which is then multiplied by a parameter matrix plus a nonlinear transformation of the activation function to obtain a matrix of aggregated neighboring vertex features. The reason for adding a unit matrix to the adjacency matrix is that we want to preserve the vertex's own feature information when propagating the information. The normalization of the neighborhood matrix is to maintain the original distribution of the feature matrix during the information transfer process, and to prevent large differences in the distribution features between vertices of high degree and vertices of low degree. In layman's terms, the main task of the Gcn is to allow each node to get information about its neighbors and aggregate it to its own embedding. This figure shows the basic principle of how Gcn works, aggregating node features in the vicinity of a node while keeping the graph structure unchanged, learning the features of the node through weighted aggregation, and transforming the C-dimensional variables into F-dimensional variables through the hidden layer. The dropout part. At forward propagation, having the activation value of a neuron stop working at a certain probability p can make the mode more generalizable because it doesn't rely too much on some local features. For the semi-supervised classification problem, the expected cross-entropy on all labeled nodes is used as a loss function. The loss function cross-entropy loss is similar to NLL loss. The only difference is that it does softmax for us. So we have that cross-entropy loss is similar to the combination of log softmax and NLL loss. Since log softmax has been used in the calculation of output, the downstream function of the calculation error should become NLL loss. Now let's go to the code part. We use pytorch to implement the model. First, we define the Gcn model. And this model shows the realization for forward propagation. And this is the test part and the calculation of the accuracy. This is our model performance. We set the epochs for 500 and run 10 turns and get the final test accuracy 72%. And why Gcn works? First, extraction of graph structure information. The advantage of Gcn is that it uses labellation convolutional kernels to extract the spatial structure information in a deeper level. Second, semi-supervised learning. Semi-supervised learning combines the overfitting and unfitting tendencies, respectively, of supervised and unsupervised learning, creating a model that can perform classification tasks excellently given a small amount of labeled data and a large amount of unlabeled data. Conclusion: we perform node classification on ogbn-arxiv dataset using Gcn, and the result turns out that Gcn achieves a good performance on this task, capturing node features on its neighborhood as a semi-supervised learning method.